So, welcome to Cooking with Unity. I'm your host, Maximilian Moreau. And first of all, today's episode, we're not going to be continuing on the puzzle platformer. I'm going to be putting that off for another week just because I didn't really get a good chance to play around with what I was going to do with for the next episode, and I didn't do great last time on a dry run. So, we're going to not do that for today. And instead, I'm going to do an overview of some scripting basics with a focus on transform and vectors. There's On the previous projects we do a lot of movement. Movement is like the most important thing that you're going to be doing in games, and I just kind of blow through it in most of the episodes and just I know most people have been able to follow along and copy down the scripts, but I have a feeling that most people don't actually really understand what's going on behind the scenes. So this is going to be a little bit of a primer, and it'll allow me to go over this in a little bit less depth in the later episodes, hopefully, and hopefully you'll be able to understand what's going on. And the other thing is, like, I've only had a couple hours of sleep last night, so this would not be a good episode to continue a project on. So I should still do the full hour today, but if I'm not feeling it at about the 30-minute mark, I may call it early. So let's see what we're going to start with and just start playing around. So every object in Unity has a... Let me get the microphone a little bit further away. It's cutting out. Every object in Unity has a transform. And what a transform is it describes a object's three-dimensional coordinates. That's basically what it does. So we're in a new scene here, and our camera has a transform. It's attached up here, and it also has a camera and a few other things. But like, even if we just make an empty game object, it has a transform. There is no such thing as a game object in Unity that does not have a transform. All the objects have position. You don't necessarily have to use the position information, but it's there. And so a lot of times you'll want this information. You'll want this, but occasionally it'll be ignored for like manager types and stuff. You'll probably just have them laying out wherever, and it doesn't really matter where they are, just as long as they exist. But in most cases, you're going to be using it because it's what describes where an object is. So I'm going to delete this empty game object. And we're going to create something that actually has a renderer so we can see it. So I'm going to create a cube, our friend the cube. And I'm going to set it to 0, 0, 0. So what these numbers represent are the position relative to the origin, at least for objects that don't have children. I'll go into the child relationship here in a second. But basically, this describes the object in the world coordinates. So the X position, if we use the default camera position, X describes the left and right coordinates. Less is further to the left, more is further to the right. So if we set the position of this to, well, we can just slide it. You can see just by sliding it that as it goes positive, it goes further to the right. As it goes negative, it goes to the left. Y, same deal, except for up and down. And Z is harder to tell from here, but it's the actual depth of the object. And these are based on the world coordinates. And depending on where your camera is, your point of view of this may be completely different. So if our camera was on the other side, if we were to move the camera and flip it around 180 degrees, you'll see that moving the cube, when I move it to the right... Oh. Did I not save that? Oh, I did. I think I did. So... moving left and right, those are the same still. There we go, that's opposite. Oh, I see, I rotated on the wrong axis. Let's do 180. So now we're looking at the opposite side. And so y is still the same, but x now goes to the right and to the left. It's actually still going the same direction relative to the world, but the camera's position has changed. On all our projects, well, on the first project that we worked on, we had a fixed camera angle, so we didn't have to worry about the positions being different. And on the second project, it's a first-person game, so the camera's constantly moving. So the camera's location may not, the way objects move relative to the world will be different based on where your position is, or at least it'll look different. It's actually describing the same data. So I'm going to put this back to where it was. And so in almost all applications, you're going to need to move objects around. And there's a bunch of different ways to do this. Ultimately, what movement means is that the transform is going to change. The actual position information in the transform is going to change. So we're going to create a new C# script. I'm just going to call this move test. And we're going to open it up. Cue the Jeopardy music. It is amazing how slow computers can be when you want them to not be slow. All right, so come on, open the actual project. There we go. All right, so here we are. Our basic script has start and update already filled out for us, and what we're going to be mostly concerned with is update, because we're going to be describing motion. And in the first episode, we did something similar to what I'm going to do right here. We're going to be vector 3 new position equals transform dot position. Actually, let's talk more about transforms themselves first before we go into this. So we have our mono behavior here. This is a when you create a new C# file, it automatically creates a child mono behavior style object, which has a bunch of stuff that's set up for us to manipulate objects. So this script is designed to be attached, as most scripts are, attached to objects in the scene. And we've done transforms before where we change the position, and to get at our transform, it's lowercase transform. And what this actually means is this is the container of all of the transform data, and it also has functions to work on transform data as well. If this script was attached to this cube, transform contains all the data that's already in this cube and can be manipulated as well, so you can change the different aspects of the transform. And this is actually a shorthand. It's a shorthand for game object, which is whatever this is attached to, dot transform. It means the same thing. I think that directly accessing the transform is actually slightly better performance-wise, but it's probably close to negligible in either case. But almost everyone uses the shortcut. So most of the time you're either going to be using built-in variables and objects, or you're going to be making your own variables. And so transform is always there. If you have a mono behavior, you have access to this. You don't have to attach anything special. It's just ready to rock. And the most basic information out of this is the position. So if you do transform.position, you'll see here it says Unity engine.vector3 vector3 position. So this is a vector 3 that describes the location in 3 space. And vector 3s have 3 components, x, y, and z. You can actually access each of them individually in here as well. So X, Y, and Z are in there. And you can't directly, you can set the position to another object. So now I'm going to go say what I was saying. So you've seen this before where we have a new position object, this vector 3, and then we do something to new position, like new position dot y plus equals, we'll just do 1. We'll just do 1.0f. Actually, yeah, that's going to be too fast. 0.1f. And then we set the transform dot position equal to the new position. So what this means is we set new position to equal to transform dot position. So if we're talking about this cube, it's going to be all zeros. And then we take the y component, which is 0, and we add 0.1 to it. So now the y should be 0.1. And then we set the transformed dot position to the new position. So update runs every frame. And what that means is this will constantly be changing because the transformed dot position is going to be where it was the last time we changed it. So the y will just creep up over time. So if we attach this to our object will just start moving up. Let me go ahead and do that and make sure that that's working. So we should see it move up. Yep, there it goes. Just starts moving up and keeps on going. So this is one of the most explicit ways you can move things around, where you actually just play around with their components. And this works for really basic cases. A lot of times you're going to need to do more vector math, linear algebra stuff, as opposed to just setting coordinates. So I'm going to try and go over that a little bit here. So vectors are, what they actually are is a descriptor of a direction and a magnitude. If you ever see vectors drawn in a diagram, it's usually just a little arrow. It'll just look like, something like this, although it'll look in whatever direction you're going. Probably should have an art program, but I'm terrible at drawing, and I'll probably do better in ASCII here. So when you have a vector, it describes a direction and a magnitude. And so technically, points in 3 space usually are described with 3 coordinates, so the x, y, and the z. And that actually can be thought of as a vector. A point can be thought of as a position described by a vector originating from the origin. So you can't see, the origin's not explicit. Maybe I should make a little, okay, we'll just use our game objects here. We're going to call this, we're going to remove the move test script. We're going to call this origin cube, because it shows us where the center of the world is, basically. And so objects, if I create a new, well, I'll create a sphere this time just to mix it up. Actually, let's make the sphere the origin sphere, and let's actually make it be at the origin. And let's move this cube over in the x direction. So this object, and actually let's just move it in all 3 kind of arbitrarily. So this set of numbers can represent a vector, and the vector is basically a line drawn from the sphere to the cube with a little arrow on the end so that you know which end is which. That describes this offset from the world position and the world origin. And so that describes one thing, but you can add vectors, you can subtract vectors. There's other operations you can do on vectors that I'm probably not going to get into on this episode. But the important thing is vectors can be added. Let's start with that. So instead of describing, instead of changing new position.y, this will move up relative to the world always. And a lot of times you'll be working on games where the movement will be relative to the way that the character is oriented. And so you might have times when you want to move it up relative to a different point. And am I going in circles here? Let's just do a vector math version of this so that you understand what I'm talking about. So instead of doing the new position thing, we can do let's create a variable called public vector3 movement direction. And this will, as I said, it describes direction and magnitude. We're going to probably be using both of on these. So instead of just creating this temporary variable and stuff, we've already got a movement direction variable. We're going to just say transform.position plus equals movement direction. And we're going to go in here and attach this to our cube, which we're just going to call cube. And we're going to put move test on him. And movement direction shows up here, and it's got an X, Y, and a Z, and this describes the vector. So if we wanted to do exactly what it was doing before, we can set Y to be 0.1. And when we hit play, it should start moving up at a rate of 0.1. So there it goes. 0.1 per frame. So this is one component of it. So if we wanted to move in the X direction, we could do the same thing. We do 0.1, and that describes an arrow that points to the right, and it follows that. Each frame, it adds that position to it. And Z, same thing. If we set this to 0.1, it'll start moving into the screen depth-wise based on our current camera position. Well, it's always going to be moving that direction to wherever the camera is, but our current camera position, it's into the screen. So now we can actually describe two components or three components at once. So if we set all these to 0.1, it'll move at a angle that's into the screen, to the right, and up at the same time. And see, there it goes off into the sunset. And what's actually happening here is the individual components are being added together. But that's happening behind the scenes. That we can just add, vector classes have the ability to be added together just inherently, and it does all the work for you, all the dirty work for you. And so this is another way that you could change directions and move things around. So this ends up being more useful in the general case. You're generally not going to want to be breaking things into their individual components when you can just have a vector. Even if you only want one component, you can always just use a portion of a vector. Like you can just do one of the three components. And there's a lot of built-in vectors that you can get at too. So like, say we wanted to make a version of this that just moves up. All it does is move up. And so we know the direction is going to be Y, positive, right? And we only care about the amount that it moves. So there's useful vectors that are built into the vector3 class that I'm going to show you here. We're going to just do public float speed. And what this one is going to do now is it's going to move upwards in the Y direction. So we could do transform.position plus equals vector3 dot up. And what vector3 dot up is is a supreme-made vector. It all it means is 1 unit in y, 0 units in x, 0 units in z. So if we were to make it in our little variable here, which is going to go away shortly, it would be the equivalent of this. That's what the unit vector up, and it has a length of 1. All the unit vectors have a length of 1, which is a useful number because it means that you can multiply a scalar on that. So speed is our scalar. Vectors can be added together, and they can be multiplied, and they also can. We're not going to get into vector multiplication on this episode because it's matrix math, and I don't have a firm enough grasp on it to teach it right now. I mean, pretty firm grasp, but I wouldn't know really where to start. So what this will do is our speed will determine how strong this vector is, how much magnitude this vector has. So if our speed is set to 1, once we save this, this should update. All right. So at speed of 0, it's not going to do anything. At speed of 1, it'll be moving up 1 unit, and that'll be really fast. And at 0.1, it'll be doing what we were doing before. And actually, negatives work as well. So, like, if you do negative 0.1, it'll move in the opposite direction as you expect it. So, unit vectors are really useful. Like, 1 is a useful number because of the fact that you can multiply any number, any real number with 1, and you'll get that number back again. So all this means is we're just getting whatever we put in as speed is what we're getting, but in the y component. There's one of these for every direction. There's vector 3 dot up, which is just the y component. Vector 3 dot down, which is just the y component negative, so it's negative 1 y. Left, which is negative 1 x. Right, which is positive 1 x. And then forward and back, I think is what they're called. Forward, yeah, which is positive 1 x, z. And back, which is negative 1z. And all of these are pretty useful. Also, any vector itself, like this is all world space relative here. So if you want something relative to its own orientation, you can do that too. So like if we take our transform dot, we can get the up on the transform and the down on the transform. And what these mean are, oh wait, I guess it doesn't have down. Up, right, left. All right, so that's funny. Most systems don't actually have a separate left and right. They just have right, and then they expect you to do negative or forward, and then they expect you to do negative for back. And evidently that's the case here. When you're doing it relative to the game objects transform, it doesn't look like they have the helpers for left and down and back, but they do on vector 3. That's interesting. So if you wanted left, you could do right times negative 1, and that would be 1.0f, and that would be moving to the left. This statement doesn't mean anything, which is why it's underlining it and saying I have spelling errors or whatever it is doing there. So what this means is based on orientation, we can move things around. So a lot of games, you'll have objects that are rotating as well as moving. So let's actually create a child object for this cube so that we can get an idea of where it's pointed. Typically, in most games, you're going to be most focused on forward. You can always get away with the other directions, but I typically use Z as my forward just because that's built into the system as it is. And so anytime I have an object that I needed to face a certain direction, I always have it face along Z. So we're gonna make our cube have a. Do we have a cone in here? No, we don't. Naturally, we're just gonna create another cube, and this one's going to be called direction cube. So this is just gonna be a little face for our cube, basically, and we're gonna make it smaller, about 0.5, 0.5, 0.5. And we're going to attach it so that it's at the front of our cube. Now, when I drag this into the cube here, it's now a child of this cube. Now, these coordinates that you see here, even though it doesn't really show anything different here, they no longer are relative to 0. So what I mean by that is, if I just set this to 0, 0, 0, you'll see that instead of being inside of the sphere that describes our origin, it's inside of our cube. And that's because this is the relative position of the object compared to its parent object. And in the case of objects that don't have parents, it's their position relative to the world origin, which is represented by our little sphere here. So if we want this direction cube to be in front of the cube in the z direction, all we have to do is set the z to 1, and it'll be in front of the cube in the z direction. And now if we make any changes to the cube's orientation or position, it will take our child with it. The child's relative position to the cube does not change, but the cube's position changes, which changes the child's position. And sorry if that went over anyone's heads, but yeah, we're working through this. So now that kind of represents the forward of it. So our cube kind of has a face, and you can rotate the parent, and it'll rotate the child as well. And so you can see kind of where it's facing. So I'm going to rotate it so that it's facing up relative to the camera. And we're going to change our script to... Wait. Did that work? Oh, I see. So when we rotate this up, I'm currently showing the global axes, but you can actually set this to local, and you'll see when you rotate it, it will rotate the arrows to describe the position as well. So this is another way you can see where something's facing. So we've got our blue arrow represents the Z, and now it's facing up along with our, you can see the little position thing there. And we're going to change our move test script to move via, it's just going to move forward. It's a certain amount to move forward. So transform dot position plus equals this time instead of using vector 3 forward, so let's do that first. So vector 3 dot forward times speed. So what this one's going to do is vector 3 forward, as I said, gives you the world coordinates, so the world Z. So if we hit play on this, it will start just moving into the scene, or out of the scene, I guess. Do we have our speed as negative, so that's the reason. So our speed is 0.1, it should move into the scene. And that's not the way our cube is facing. We want to pretend this cube is a ship or something, and we want it to be able to move around. So what we're going to do here is, instead of doing vector 3 dot forward, we're going to do what I was talking about earlier. We can do transform dot forward. So this is the vector relative to the object itself, as opposed to relative to the world. And so what this will mean is it'll move along wherever Z is pointed. I didn't actually hit save, did I? Nope. All right. So we hit save, we hit play, and we'll see it's moving up. There we go. And you can change the rotation, and it'll just continue following along in whatever direction we've rotated. Okay, Y doesn't mean anything. Oh, Z doesn't mean anything anymore either. Gimbal lock. All right. Watch those gimbals. So let's see what we got. Y is not cool. Z's not cool. Nothing's cool. It's because we already have -90 here and it's causing us troubles. So, let's see. So what this z vector is describing is it's a transformed z vector that now has a different, like, it's actually describing y at this point, but it's relative based on the object. Does that make any sense? All right, we're at the 30-minute point, and I'm not too tired, so I'm gonna keep going. I'm gonna let's see. We're gonna make it so that our object will follow the mouse around, and we're gonna be able to do a little bit more vector math, and I'm gonna be able to show you some more useful things. So we're gonna do some vector subtraction, and vector subtraction is incredibly useful. Let's go ahead and make this thing kind of move the move around via the mouse position. Actually change its position here a little bit so it's in the center, and we'll just keep the sphere in there so as a reference. Let's make sure everything still works. All right, and actually I'm going to put a light in the scene just so things look a little bit better. Directional light, and we just want it someplace that we can't see it in the scene so it's not bugging us. And so now we have a little bit of depth and a little bit, you can see that it's a sphere better. We're gonna move the mouse, move it around using the mouse, and is this too complex? No, let's actually use some other object's position. So create a we're gonna create a capsule just because we haven't done a capsule yet, and we're gonna put this somewhere in the scene. We're gonna put it over into the left here and in a little bit deep. And see if we can see it in the scene. Okay, we can. So let's have it so our object just going to teach what I want to teach. Well, let's see if we can make this object move to the capsule. This might be useful for a multitude of things. And let's just go ahead and make a new C# script. We're going to do move to object, and we're going to do kind of a basic implementation that doesn't take direction into account or anything, and then we're going to do an implementation where it actually points at the object and continually moves forward. So let's start with the basic one. So we want, we're going to do another public float speed. And what this script is going to do initially is we're going to have this move the object toward goal object at set speed. And so we're going to need a goal object. So we're going to do a public game object goal object. And so we now, instead of having a vector that we've set or a relative vector, we have an unknown. We want to find out what direction we have to go to get to that cylinder. So this is a job for vector subtraction. And so what I mean by this is these two objects are described, their positions are described by two separate vectors. This one's vector describes 0, 0, 0, which is at the origin. I'm going to actually move it a little bit off the origin again, just to illustrate things a little bit better. -1, we'll just put it so that's right there. So this describes our world coordinate, and this describes our world coordinate, and these are two separate vectors. And the thing that's useful about vectors when you're doing subtraction is this vector from the origin to the capsule here. And if you were to take that vector and subtract the vector that describes this object, this off from the origin, you'll get a vector equal to I forget which direction it faces, but you'll either get, depending on which one you subtract from what, you'll either get a vector that points to the capsule or points to from the capsule to the object. Now this vector doesn't have a position, but you can apply it to any position and it'll change that position. So what we're going to do, and actually it's, so like if we take this vector, subtract this vector, you'll get this arrow pointing towards the capsule. And so what this means is if we were to just do transform dot position equals, actually plus equals goal object dot transform dot position minus transform dot position. Does this make any sense? So what this will mean is it should just jump right to the object. This is not going to be terribly useful as is, but let's see what it does. Oh, we still got the old script on there. So remove this one, move to object on here. Speed's not currently being used. We're going to set our goal object to be, this, what is it called, capsule. We're going to call this capsule goal. And so we've got our cube. We throw goal for the goal object. And we hit play, and you'll probably just see, yeah, it just snapped to its position. And the reason it did that is because the first time this runs, it is getting that vector that I was describing and then adding it to its position, which will put its position exactly on top of the capsule. And then every subsequent frame, it doesn't move at all because since they're the same position, when you subtract a vector from a vector and they're the exact same vector, you get 0. And so there's no motion after that point. So we have a speed here, so we can multiply this in as a scalar. So we're gonna put these in brackets so that we know the order of operations, and we're gonna multiply it by speed. And so now if we set speed to, say, let's do 0.1 again, we'll see the object move, and it's not moving at a set rate right now. And the reason is the vector that we're multiplying the speed. Before, when we were multiplying the speed, and we had a unit vector, and that unit vector has one length, and so each frame this is getting closer to the object, so the vector that we're multiplying becomes smaller and smaller, and so you can see it's still moving very slowly to that position. It has effectively reached that position now, but it creates this kind of like logarithmic movement where it just moves a little bit slower as it goes. And we don't want that. We want it to be constant. So there's this concept of normalization. Sorry, not normals, but normalization. There's a mathematical function you can do to a vector that will make it so that the vector continues to point in the same direction it was pointing before, but its length will be exactly 1 unit. Now, I'm not going to go into the actual formula for that, but in programming, typically you don't have to do a lot of the low-level math. You just have to know how the math works. It's like having a calculator with you at all times. Like, you don't have to know how to add 3 and 8 if you know that pressing 3 plus 8 on a calculator will add the two numbers together. Obviously, everyone can add 3 plus 8, or most everyone can. But you think of it at a higher level than that. You're thinking of the problem as opposed to how what's actually happening in the background. So all vectors classes, all vector objects in Unity and in most engines for that matter, have a normalized function. So we can do transform.position as this is a vector. We can do dot normalized, and that will return the direction of the position with one unit vector. And we can do similar stuff here with our other vectors. So this is a vector, and this is a vector, and we're subtracting it, and it returns a vector. And so you can actually put a dot here and do something as if it was a vector, because it is. So we can do normalized, and what this means is it will magically, you don't need to know how it works, but I encourage you to learn this actually, but what it's doing is it's making it so that the vector still points in the direction, but has one unit as length. So all of a sudden this will work like it did before, and actually give us a linear result. So when we hit play, you'll see that this thing now moves at a set rate to our goal, and then once it reaches the goal, it stops. So that's exactly what we want. And I guess it doesn't stop because it's probably overshooting the target slightly and then going slightly back, because now the actual amount that it moves is based on our speed, and so it's going to overshoot a little and then overshoot a little bit back. But effectively, it got there. So that's vector subtraction. That's the main thing that vector subtraction gains you, is just being able to figure out a vector between two objects. I was pointing at my screen, and I just realized you totally can't see that, so I was pointing at both these objects. Let's change this script around a little bit and use orientation to guide our little cube. And so we're going to be doing something similar to the moving straight up thing that we had in our move test. And actually, I'm going to go ahead and create a separate C# script for this again. We're going to do move, rotate toward object, and move forward. So what this one's going to do is it's going to actually, just like we did before, we're going to set up a speed, public float speed, and we're going to set the position based on its forward. So transform.position plus equals our forward vector, so transform.forward times speed. So again, what this does is, if we were to attach this to our cube, we're going to remove our old movement script here, and we set it to 0.1, it's going to move up. And again, this is how we had it set up, so if you rotate it, it will move in a forward direction no matter what orientation. So what we're going to do here is we're going to actually have this rotate towards the object. And so what we can do is we can get a vector that describes... Okay, we're going to use another helper function here. This is kind of getting unrelated to what we were doing. I'm going to do it anyway, just because this is pretty useful for people who are making objects that need to seek other objects. So this may not make as much sense, because we're going to be going into rotation a little bit here, which is quaternions, and it's kind of a different beast. than the position stuff. It's still 3 component. Well, the quaternions is 4 components. I'm not going to go into the low level stuff with the quaternions, but there's some helper functions we can do with the transform. I think transform dot look. No. Actually, it's probably in quaternion. Quaternion dot look rotation. So what this does is this returns a quaternion based on a vector. And so we need to get a vector to describe this. So this basically says, I want you to point the front of my object in a direction. And this is what we want, because we want to be able to point our cube so that it's pointed towards our goal object, and then we're going to continually move forward. So this part we're always going to be doing. We're just going to leave that in there. And so to determine that, we're going to use the subtraction again. We just want this vector here. And it doesn't matter the magnitude in this case, because we just want to be able to rotate along it. And so we can just feed it the same thing that we had in our previous test here, which is goal object dot transform dot position minus transform dot position. So we're going to do the same thing here. Public game object goal object. And so we can do transform dot rotation equals quaternion dot look rotation, and then we are doing goal object dot transform dot position minus transform dot position. So I'm gonna mention this real quick, as I didn't mention it last time. These look very similar. We've got transform dot position and transform dot position, and this one has this additional goal object. So as I said, transform dot position is actually a shortcut for game object dot transform dot position, and this is specifically the game object that this object is attached to. Any object has a transform, and so you can access any object's transform by using the object name or the reference name dot transform. And so the goal object here has a position, and we set our goal object by dragging in the object that we want. So we're going to put our goal here in again. So this is a reference to this goal. And so whenever we say goal object dot transform, is whatever goal object is set to, we want its transform. And so I'm going to go back to the shorthand again for the local stuff. But so this is a different transform. Even though it says transform, it is a different transform than this transform. This one belongs to the goal object. This one belongs to the object that the script is attached to. And that's probably kind of confusing, but every object has its own instance of transform, and it's all going to be called transform. And so it's just a matter of which object's transform you're looking at. So this should actually be all we need. Let's see if this actually works. So this will just snap and immediately start heading towards the goal. See, it's pointed out the goal and it's heading towards it. That's good. So sometimes you want this to, we're kind of getting more into game mechanics again, but I want stuff to move around and it's more useful for you guys anyway. So sometimes you want things to not instantly rotate like that. So we could have a public float rotation speed. And so what we can do is there a quaternion lerp? Of course there is. This is a useful engine. All right. So we actually want the we actually want this to slowly rotate towards the goal direction as opposed to just instantly rotating. So this if we were to move the object, it just instantly updates. So if we have the goal object here, and this is what's cool about this, we can actually, take this thing and we can move it, and you'll see that the object will follow it, and it follows it relentlessly. It will instantly, if the object is on one side, one frame, it will move to the other side instantaneously. And so we want to make that go over time. And lerps are linear interpolations. What that means is you'll have a start point, an end point, and a time. And based on the start point and end point and time, it determines what the value should be. So our start point is going to be our current rotation. Our end point is going to be the desired goal rotation, which is our vector that describes goal object. So this is our goal, and our initial is just transform.rotation. So what we can do in a very basic sense is this is kind of, we've got 10 minutes left, and I'm not sure if this is the appropriate thing to do. Yeah, let's not worry about this right now. We'll do that. We'll do that in another episode when I have more time to describe linear interpolation. And actually, so I can describe. Honestly, the main thing is I don't want to go into coroutines right now, and this is a really great case for a coroutine. There's 10 minutes left. I'm just gonna do it. I know I said this was high level overview and kind of more in depth overview on things, but. I'm just going to throw this out here so that you can kind of see how it would look. So we haven't done a coroutine before, and I'm going to do one right now. IEnumerator. All coroutines in C# have to return an IEnumerator. This is how it actually works behind the scenes. And we're going to do rotate over time. And we're going to have a goal position, so vector 3 goal position. Actually, no, it's just going to be the angles. So start angle, this is going to be a quaternion. Quaternion end angle. And does this make sense? Okay. Yeah, we'll just do float time. So that'll be how long it'll take to rotate to our goal. And all this is going to do is it's going to, while oh god, this is getting too stupidly complex for what I was trying to show. I'm just going to do it real quick anyway. So while start angle does not equal, okay, while start angle, no. Okay, yeah. Float current time while current time is less than time, transform dot rotation equals quaternion dot lerp start angle end angle and then time is going to be current time plus current time divided by time. So what this will do is, if we set the time to say 10, it's going to, lerp basically uses between 0 and 1 to describe time. At 0 is at the start, at 1 is at the end. And so we can get a 0 to 1 based on the ratio of current time to time. So the amount of time is time, and that's, so if we set that to 2 seconds, if we were at 1 second, we're halfway through, so that'll give us 0.5 in this case, and that'll be halfway through the transformation. And then if it's equal to, if current time is equal to time, it'll be 1, and that'll give us the end of it. So this will just do this over time, and it'll just kind of do it once, which isn't really what we want here, but I'm just throwing this out here. Yield return null. So what a coroutine does is, and I know this, I'm just throwing this at you today. I probably shouldn't have, but whatever. What this does is, it's a function, but when you call it, it automatically gets called every frame, and when it gets called, it once we start it. So we got to start this coroutine first. So we're gonna start the coroutine at, so start coroutine, rotate over time, and we're going to do transform dot rotation, and then the goal will be this right here. You don't need the semicolon. And we're going to make the and the rotation speed. So I'm going to actually change this to rotation time because that describes it a little bit better in this case. Rotation time. And it's underlining it because I've done something wrong. So rotate over time. Transform.rotation, quaternion.look rotation. Oh, we need one more of these. One too many. So this will just start at the start, and it'll start moving over time, and hopefully this will all just work. And so now, instead of setting the rotation here, it's just going to be set in the, it's already set in our little rotate over time coroutine. So let's see if this actually works. We're going to set the unassigned local variable current time. Oh, equals 0. Oh, and we forgot to actually update the time. So current time plus equals time dot delta time. Again, this is one that we've done before. This is the change in time since the last time it was called. So this will update our little timer in real time. So we've got our cube. We're going to look at the, we're going to set the rotation speed. We're going to, rotation time, we're going to make it rotate over the course of 4 seconds. And if we hit play here, so there you go. So now you have the object, and that didn't do exactly what we wanted because, as I said, we were setting this up wrong. But at least we got kind of an interesting behavior out of it because it basically tries to rotate towards this, but since it's constantly moving, it's going to be off on it. Like, if we were to make it so that it didn't have any speed, it'll just rotate and look at the, we'll see it rotate and look right at it and stop. So that took 4 seconds. So if we do 1, it'll do it really fast. Yep. And it just automatically rotates there. So again, kind of a tangent. Anyway, at least it's kind of a cool behavior, and we'll go into it a little bit more later to make cool behaviors. I'm sure that there's going to be games where we have more AI stuff. AI is the funnest stuff to do. It really is. So anyway, thank you for seeing my show today, And sorry we're not working on the puzzle platformer today, but that'll be next week, and hopefully I'll be better rested and better prepared for a nice, strong episode of Cooking with Unity. Um, remember, if you want to contact me, why does this default to just such small text? Where's bigger? Font. Okay, it's just Command plus. Plus. If you want to contact me at pushypixels@pushypixels.com, and on Twitter it's Dragfire, and yeah, send comics suggestions, hate mail, fan mail, whatever you want. And thanks for tuning in to Cooking with Unity. Good night.